And today we will talk about the development and some interesting failures in the SULZER RND Series engines. So, in this series of engines, they offer the 680mm bore, 760mm bore, 900mm, and 1050mm bore. These four types of engines. The largest one, which is the RND 105, which means the 1050mm engine, has a 4,600 brake horsepower per cylinder at 108 revolutions per minute, and its ignition pressure is at roughly 84 bars, while the compression pressure roughly 63 bars. This gives a mean effective pressure of roughly 12.3 bars. So, let's take a look at this first picture here. At the right side, we have the older version engine, which is a SULZER RD series. At the left side, it's the RND series we will talk about today. So have you noticed any difference between these two engines? Major differences. Okay, I can see that here is a very special component which won't be seen in nowadays engines. Okay, I would replenish that the R&D series engine is actually developed in the last century, maybe 70s or the 80s, and nowadays there are only roughly maybe 40 to 50 such engines still running among the world. So this is already a very old engine, and this is its ancestor, I would say. Also, here is the exhaust manifold, which is often used in nowadays marine engines. So from these two differences, we already know that this is a constant pressure supercharged engine. This is a post-charged engine. So what is the difference between these two types of supercharging? Is that this one only uses the thermal energy. Okay, the thermal energy, the pressure energy inside the exhaust gas, while this one utilizes the kinetic energy and the thermal energy inside the exhaust gas. These two engines both are the cross-scavenging type. You can see the exhaust ports, scavenging ports, exhaust ports, and scavenging ports. So why they need such a rotation valve here? This is because that if you have a post supercharged engine, you definitely won't want the exhaust pulses from other cylinders to re-enter this cylinder which is undergoing the scavenging process, right? You don't want a high back pressure or the exhaust gas to flow reversely inside. So you have such a valve to close or isolate the turbine nozzle area and this certain exhaust pipe here. Also, the main difference between these two engines is that while you have a low load operation or you just started the engine, in this constant pressure charged engine, you don't have enough energy to drive the turbine. So that's the reason you need a accelerate blower, or sometimes they will utilize the lower part of the piston space together with this crankcase area, crankcase room, as a separated pump. During the low load operation, the supercharger and this I would call it the piston underside pump will be in series connection. Actually, the turbocharger is at the front side, and then the charged air will be pumped into the piston underside pump and be compressed for the second time before entering the scavenging space. and during the high load operation, these two pumps will be parallel operated. And in such an engine, you actually don't need such an arrangement. The pulse has already have enough energy to drive the turbine at low load operation. But this one has its benefit, I would say. In this arrangement, you don't need to worry about the firing order, because in such an engine, you need to worry about the firing order not only because the balancing, but also the arrangement of these individual exhaust connections. You won't want a very long connection because that will be kind of a constant pressure supercharging, because the long length will increase the volume and suppress the pulses, right? So you need a very short individual connections to the turbine, nozzle area, and the individual cylinders. Also, in such an arrangement, since the velocity of the gas inside the manifold is largely reduced, if you have a broken piston ring, it won't enter the turbine. That's as possible as in such a post arrangement, I would say. Okay, let's move to the next picture. This is a very interesting picture, I would say. It clearly shows the exhaust the combustion chamber components temperatures in degrees Celsius. Okay, so the first RND 105 engine is actually made in the Mitsubishi shipyard in Japan, and the second set of such engine is actually manufactured by the SULZER company itself. So during the development, they have seen the crackings and burn off of the material from the piston fireland. I would call this part of the piston the fireland. And the reason for this is actually the vanadium oxide and the sodium oxide have from the marine heavy fuel oil, because the heavy fuel oil is actually the residual fuel from the petroleum industries. The vanadium, aluminium, sodium catalysts are used as the fracking catalysts in the petroleum industries, so the residual fuel definitely have a higher concentration of such compound, and the vanadium oxide and sodium oxide combined with the steel, if the ratio is, I would say, it's proper, then the melting point can be as low as 535 degrees Celsius. And if such a compound exists on the piston fireland, and if the temperature of such area is over the melting point, then such a component can be melted and blown away by the exhaust gas flow. So because of the revisioned cooling passage inside the piston, you can see that the maximum pressure, I believe is this one, is still lower than the melting point of such a compound. By the way, such a piston is still water cooled, but I would say the nowadays engines, they are mostly cooled by the lubricating oil. You can imagine, because if the water coolant has somehow get into a leakage, the sulfur from the fuel can actually combine with the water to generate the sulfuric acid, which can corrode the metal parts in the crankcase, which is a very bad situation. I would say, but nowadays the fuel still contains such catalyst compound, which can lead to such a burn away of combustion components like the valves on 4-stroke engines, valves on the two-stroke or something else. Even the fire line cracking sometimes still happens. So what you can do to prevent it is that you have a better piston cooling. This is needed by cleaning the under this side, the inner side of the piston fire line, piston head. Sometimes they have the fouling built up there by the overheated coolant, both water or the lubricating oil. And also you need to have a correct injection timing. Retarded injection definitely leads to a higher temperature because the expansion ratio is lower. Also, the fuel injector needs to be checked regularly to get finely atomized injection. Let's move on. This picture actually shows the revisioned new nozzle here compared with the previous version of nozzle. The previous version of nozzle is actually fixed or tightened to the injector body by a union nut here, like this one, but it's very inconvenient to handle such a connection. So in the later version they use many expansion screws, precision screws, to hold down the nozzle to the main body. This is an interesting picture, and I would talk about the scavenging process later in this video in detail, but this picture actually shows the development of the RND 90 series engine, and this is the first version of the cylinder liner scavenging ports fouling. On such a fouling, you can see these are the fouling, and I will show you a picture of the clean scavenging parts like this one. So the fouling is actually caused by the incorrect valve timing. What actually they did to fix this fouling problem is that they compared this liner to a very good condition liner from the RND 105 engine, and they found that the difference between the parameter of these two engines are actually the amount of gas exit from the cylinder before the scavenging ports are opened by the piston. So in the RND 105 engine, which is a good condition cylinder liner, this ratio, which is like the gas exits out the cylinder compared to the gas exits from the exhaust ports before the scavenging ports are opened to the gas, the total amount of gas inside the cylinder is 0.4% in the good condition cylinder, and in such a RND 90 engine, unfortunately this ratio is 0, which means that even the exhaust ports are already opened by the piston. Because of the back pressure in the manifold and the incorrect timing, no gas has been exited from the cylinder before the scavenging ports are opened. So you will definitely have some kind of a contamination or backflow into the scavenging room, even lead to maybe scavenging fire sometimes. So what they did is that they moved the scavenging ports several centimeters lower, which will lead to a larger expansion ratio, and a larger expansion ratio actually leads to a lower exhaust pressure, and when the piston uncovers the scavenging ports, no backflow is happening here. And let's talk about something more, and I will talk about the scavenging at the last of this video. So this thing actually shows the nozzle for the RD engine. You might still remember that in the first video we have talked about this engine, the rotation exhaust valve controlled engine, right? So this is a nozzle, the first revision of the nozzle for RD76, which is 760mm bore engine after 2000 operation hours. And you can already see some corrosion along this surface here, right? This is definitely not good. What they did is that actually they were using the stainless, not the stainless steel, sorry, stainless alloy, stainless number 6 alloy, which is actually the cobalt alloy, being painted. I believe it's kind of a plasma painting or something. I'm not sure, but it's kind of a painting of such a stainless number 6 alloy at the outer side of the nozzle, and actually you can see after roughly 2000 operation hours, this compares very good to the previous one. Okay, nothing too much. Okay, this is the RD engine cylinder head, and this is the stress level of different locations in this cylinder head, and this is the cylinder head, definitely a revision one for the RND series engine, the same bore engine, and this is the stress level of different points. Okay, this is the thing I would like to talk about. Yeah, this is the last thing I would like to talk about. So sorry, I made it too large. Yes. Okay, so actually this is a scavenging efficiency against the air delivery ratio. The air delivery is actually the percentage of the air delivered to the displacement volume. The first thing you need to notice is that this ratio is actually the mass ratio, or you can transfer it to a volume ratio if the delivered air and the air charged into the cylinder are assumed at the same temperature and pressure, or you can actually transfer them. So, but I would say this is actually the mass ratio of the air, not the volume ratio, because the volume ratio is actually useless, because here we are more concerning on like how much amount, the mass amount of oxygen we can use to burn our fuel in the cylinder. That's the reason we have such a, I would say this air delivery ratio, also to the break mean effective pressure here. This actually, I would say these numbers are actually gained from the fuel oil consumption rate, but that's a more complex topic. We won't cover it in today's video. Okay, so also the scavenging ratio is very straightforward. Is the gas retained inside the cylinder over the gas retained plus the unused air. This is unused air, not the unused oxygen. Okay, the unused air already exists inside the cylinder after the scavenging has been finished. So this means the gas from the blower or from the scavenging ports, the gas passing through the scavenging ports and finally left it inside the cylinder at the end of the scavenging process, over the gas like from here and end up in here at the end of scavenging, add with the gas already inside here but from the previous cycle, or from the end of the combustion of the previous cycle. Okay, so the perfect scavenging means that the Okay, let's imagine such a situation, which is the piston moving downward, and the combustion just finished, and the exhaust parts already being opened, some of the gas already being driven out because of its self pressure higher than the ambient pressure here, and then you have a big scavenging gas coming inside, and this gas won't be mixed with the residual gas already exists here. This is a definition of perfect scavenging. Also, this gas won't directly enter without being retarded, maybe it's retaining. Okay, without being retaining here. It won't mixing, it won't being short-circuited out. This is perfect scavenging. It will just function as a piston, pushing the residual gas outside. So it's very clear that this is just like a very simple function in proportion to the delivery ratio, because you can actually imagine no matter how much the air we have pushed inside, that amount of air will actually being retained in this cylinder, right? It's very straightforward. Okay. Also, like this is the perfect mixing line. I would say this line. This line means that during the scavenging process, whenever you have a infinitely small amount of gas entering, this amount of gas will be fully mixed with the gas already inside here, and you have the next infinitely small amount of air entering inside. This amount of air will be mixed with the gas inside here uniformly. But you will notice that the more air you are pumping inside, the more diluted this residual combustion gas will be. So it definitely won't be a straight line. It's actually such a line. Surprisingly, the cross-scavenging, which is shown here, this will first turn up and then roughly turn down like this. This kind of a cross-scavenging even has a lower efficiency than the perfect mixing process. Okay, and the higher the charging pressure is, or the scavenging pressure, they are the same thing roughly, the lower the efficiency will be. Okay, this is just an interesting topic, and I would show you something I have written here. So like you can imagine, this is a piston and cylinder arrangement, and the purple line here is actually the proper cross-scavenging flow, which is shown previously, and the green line is actually the short-circuited situation. The thing I would like to talk about is that during their study, they found that if the piston is moving downward, for example, if we say that the piston moving downward and at this certain location, suddenly the normal scavenging pattern turns into the short-circuited scavenging, and then you can imagine that the piston will keep going down and then return to this certain position. What they have found is that at this certain position, the short-circuiting won't change over to the normal scavenging again, but it will keep existing here. And when the piston moves upward more, actually it needs to move up much more than the previous position. Move up much more, then this pattern can actually transition into this loop scavenging again. Why is that happening? Is that somebody did a study which is admitting the magnesium powder inside the cylinder and to visualize the flow. They found that the scavenging gas actually generates the spiral or kind of a vortex. Okay, the vortex. And the purple vortex, this clockwise vortex, the single very big vortex is generated by the normal scavenging. And if you have a short circuit scavenging, it will generate two counter-rotating vortices. And we know the vortices, they have energy, they have their momentum. So if you want to change the rotation direction, you need to add energy to them. That's the reason why if you already have the short-circuited flow, you need to move the piston up a bit more, and then to break this counter-clockwise spiral into the normal clockwise spiral and to regain the normal scavenging again. The thing that you need to keep in mind to prevent such a thing from happening, I mean definitely for the designers, is that the scavenging ports, you definitely won't want any acute changing of the angle. Also, the upper side can be such not too acutely in angle, but the lower side you prefer it to have a very acute upward facing direction to better direct the air gas flow like this way. Also, the side of the piston shape like this is also for the same purpose. And okay, sorry for that. Actually, the stainless material, you can actually see it from here. This is a nozzle for the SULZER engine. You can see the coolant hose and the fuel hose, and this is a stainless material. You can definitely see the body and the nozzle hose are the two different materials, and those had I ever mentioned this to you? I mean, there are actually two rows of spray holes and two angles, two hole diameters, which you actually see from this nozzle here. The upper row and the lower row, they have different angles, and the upper row is like 57 degrees. The lower row is the 102 degrees. Both 7 holes and the different diameters. This is also a very old engine actually, but this is very heavy, you know. Some marine engineers, they say that the old SULZER fuel valves are very heavy, like extremely heavy nozzles. Also, such kind of a nozzle are also shown in the main BMW old engine. This is the loop scavenging engine, and you can see this is a stainless material, and the main body material is a mysterious material to me. It's not steel, not iron, not copper. Mysterious material, sorry. Okay, so I would say that this is all about today's video, and I hope maybe in the future videos I would talk about the 3 different scavenging types, which is the uniflow scavenging, loop scavenging, and the cross-scavenging, which you have already seen today, and something to keep in mind while designing the scavenging process of the engines. I hope that would be covered in the future videos, and thanks for your watching, and have a nice day.